All right, so we're looking at section 8.1, inverse variation. Earlier in the year, we talked a lot about direct variation, so now we're going to take a look at inverse variation. If you don't remember what direct variation is, remember it is your equation where you have the form y equals kx, where k cannot equal 0. Inverse variation, for the most part, is going to be y equals k over x, or if you're trying to solve for x, it would be x equals k over y. Or if you're trying to solve for k by itself, it's k equals x times y, where k is your constant of variation. And so to remember, when we talked about direct variation, that meant when one was increasing, the other was increasing, and so on. They had a direct relationship. With inverse variation, when one quantity is increasing, the other is decreasing proportionally. All right? So just keep that in mind. So direct, they were doing the same thing. Inverse, they're doing opposite items, or increasing, decreasing proportionally. So here we're just talking about identifying inverse and direct variation. And so the easiest way to do this is to compare your x and y. So one of the things we just talked about is that your k value for inverse variation is k equals, in this case it'd be x times y, because we know that y equals k over x, which means we would have to divide by x. So what we're going to do to test for, in this case, x times y would be 30, so k in this case would be 30. We're multiplying the 2. Here, this is also 30. This is also 30. This is also 30. So since the product for all of these is 30, it tells us that y varies inversely with x, and that our constant of variation is just 30. So for this, we know that we could write the equation y equals, instead of k over x, it's 30 over x, and this would be our inverse variation. So this is inverse. All right, so here, same idea. Let's test for inverse first, because that's just what we're working with. So to find k, we're going to try to multiply them together. So k in this case would be 20 for this one. This one is 32. Well, that fails already. It's not inverse. I can tell you that much right now. So the other option to do, since we know it's not inverse, would be to test and see if we're dealing with direct. Well, direct variation, to find your k value, is you have to divide y and x. So let's test for that one. So that would be, if we wanted, so it's not inverse, so we'll say no inverse. So for direct, we're going to look at y over x. And so in this case, y over x would be 5. And this would be 2. So it's not direct either, so this is neither. So it fails both. All right, so for these examples, I'm not going to look for both direct and inverse. I just want to test for inverse. So remember, for inverse, we're thinking k is going to be equal to x times y. So for a, here, this would be 1.6. This would be 10. This would be 40. And so this is not inverse. So we can kind of move on. We could have moved on earlier. Same thing here. So this is 8. This is 8. This is 8. And this is 8. So in this case, k equals 8 for all of these if we're taking x times y. So this would be inverse. So our inverse equation would be y equals 8 over x. And then for c, same idea. We've got 40 times 0.5 is 20. 12 times 1.2, that is just 10. 10, this is 5. So this is not inverse as well. All right, let's keep going. Here it says, suppose x and y vary inversely and x is 4 and y is 12. We saw some of these back in previous chapter for direct. Well, what we want to do is it says, what function models the inverse variation? Well, it's inverse variation, so we know we're going to start with y equals k over x, our base inverse format. And then we're going to plug in the values for x and y they give us. It's because we got to figure out what k is. So that means we're going to get 12 equals k over 4. Well, to solve this, we'd multiply both sides by 4. So we get k equals 48. So that means our actual expression or inverse variation function is y equals 48 over x. Then what they want us to do is they want us to solve for y when x is 10. So that means we're going to take x equals 10. We're going to take our original expression here and we're going to plug it all in to see if we can find y. So y equals 48 divided by 10, which means in this case, it should equal 4.8. So y equals 4.8 when x equals 10. So here in problem 2, we want to do the same thing. It says, suppose x and y vary inversely, that's key, and x is 8 and y is negative 7. All right, so that means what function models this? So for part A, we're going to do the same thing, y equals k over x. They tell us that x and y in this case are 8 and negative 7, so that is, so negative 7 equals k over 8. To get rid of the 8, we'll multiply it to the other side, and we should get k to equal negative 56. So our equation is y equals negative 56 over x. And then we're going to skip b, we're not worrying about graphing. And c says, what is y when x is 2? So y equals negative 56 over 2. So y in this case equals negative 28 when x equals 2. All right, next problem. All right, so your math class has decided to pick up litter each weekend in a local park. Each week there's approximately the same amount of litter. The table shows the number of students who worked on it in each of the first 4 weeks of the project. The time needed for the pickup, the table shows the number of students who worked on it each of the first 4 weeks of the project and the time needed for each pickup, or for the pickup. So what we can see from this table is as the student numbers increase, the time essentially decreases. So that is a very inverse relationship, but just to test, let's investigate and see what our k value would be between these values. So if we're looking here, remember to find k with an inverse variation, it's k equals x times y. So 3 times 85 is 255. 5 times 51, well that's 255. 12 times 21 is only 252. And 17 times 15 is 255. There is this one variance here, but ultimately it is fairly close to 255. So we're actually going to just use the 255 as k. And so what this means is that we can model this using y equals 255 over x. If we were to graph this, we would see that this is once we talk about the inverse variation graphs, this is a very inverse relationship. So in this case, this is the model we want to use. We're going to take that model with us as we look at this next question. It says, how many students should there be, or what should there be to complete the project in at most 30 minutes each week? All right, and so when we go back to this model, one of the things we need to remember is that in this case, we're saying that x and y are our time and students. So that being said, let's say instead of writing it this way, let's write this using the variables they used, so we'll say t equals 255 over n. So this is what we want to use. We just wrote a very generic inverse one, but now we're using the correct form for the word problem. So as we come down here, t equals 255 over n, where n is the number of students. Well, at most 30 minutes. So let's put 30 here equals 255 times n. So we're trying to figure out how many students are needed. So we'll multiply both sides by n. So this becomes 30n equals 255. We'll then divide by 30. And we're going to get that the number of students is 8.5. So there should be, to get it done in under 30 minutes, or at most 30 minutes, we need 9 students. So let's go ahead and round up. All right. So here, after a major storm, your math class volunteers to remove debris from yards. The table shows the time t in minutes that it takes the group of n students to remove the debris from an average size yard. So once again, as the student number goes up, the time decreases. So what we want to look at in a problem like this would be to find k, because this is a very inverse relationship. We'll find k, we'll write our function in terms of that, and then we will go ahead and solve this accordingly. So go ahead and pause this, try this one on your own, see if you can figure out in at most 25 minutes, and when you're ready to see the answer, unpause the video. So after investigating through this problem, you're going to find that k is 225. So that means in this case, your function that models this is going to be, and let's use what they use there, so we'll say t equals 225n. Part B asks, how many students should be there to complete debris of an average size yard in at most 25 minutes? So if we take 25 equals 225 divided by n, we'll solve this for n, and we get that there should be 9 students. All right. When one quantity varies with respect to 2 or more quantities, you have what is called combined variation. When one quantity varies directly with 2 or more quantities, this is called joint variation. So here we have our different types of variation. When we see them varying jointly, we're dealing with direct throughout. It can be jointly and inversely. Then you have to remember that the top would be multiplication, the bottom would be your division for your inverse. And then varies directly with x, inversely with the product of w and y. So here we have various types of combined variation. And so combined variation includes direct and inverse, where when they mention the word jointly, you're thinking just multiplication for that part. So be careful, they kind of mix them together. So make sure you're reading it carefully to understand which type you're using. This question used to be multiple choice, not anymore. So the number of bags of grass, seed n, needed to reseed a yard varies directly with the area A to be seeded and inversely with the weight W of the bag of seeds. If it takes 2 3-pound bags of seeds, or 2 bags of seed, to seed an area of 3,600 feet squared, how many 3-pound bags will we need to seed 9,000 feet? So the first thing we want to do is write our variation expression. So in this case, we've got n, and we know that this varies directly with the area A, so let's say k times A, and inversely with the weight W, so we'll have W on the bottom. So this is our variation function. Then we're going to take our values and we're going to plug them in accordingly to where they need to be. So in this case, where did it go? It takes 2 3-pound bags of seed to cover an area of 3,600 feet. So we're just going to plug those in accordingly. So we've got the number of bags. So 2 bags equals k times our area, which is 3,600. And then the weight of the bags is just 3 pounds. So what we're going to do with this is we're going to solve this for k, which means we're going to multiply the 3 over. So we've got 2 times 3 here, and and then it equals k times 3,600. Then we're going to divide by the 3,600. So we've got 6 divided by 3,600 equals k. Well, in this case, when we reduce it, k should equal 1/600th, and so we'll leave it like that. And so we're going to take k, and then we're going to answer the last part of this problem. It says, how many 3-pound bags of seed will be needed for 9,000 square feet in area? So to solve this part, we're going to go back to our original expression. We need to know how many bags we need, so that's what we're looking for, n again. But this time we know our k is 1/600th, and then the area in this case is 9,000, and then the weight is still 3. So we can take, essentially, we can take 900 divided by 600, no, sorry, 9,000 divided by 600, and then divide by 3. And so in this case, n should equal 5. So we're going to need 5 3-pound bags of seed to seed 9,000 square feet. All right, so here we have another problem. This one says the number of bags needed to mulch, the number of bags of mulch needed to cover a planting area varies jointly as the area of the mulch A in square feet and the depth of the mulch D in feet. So we know we have the number of bags. Jointly in this case means we're strictly sticking to multiplication. So jointly of the area A and the depth D. If you need 10 bags of mulch, so 10 bags of mulch to mulch 120 feet to a depth of 3 inches. In this case, we're almost making a mistake because in the original problem it says the depth in feet. In this case, inches, 3-inch depth, that's 1/4 of a foot. So in reality, we're going to represent that 3 inches, 2.5 feet. So 0.25. There we go, that's better. And then they ask how many bags do we need to mulch 200 square feet to a depth of 4 inches. So we'll solve that in a second. Let's just figure out what k is in this case. I'm going to go ahead and simplify this part here. So this is k times 30 equals 10. I'll then divide by 30. And I get k to equal 1/3. So now that I know k is 1/3, I'm going to plug this back in to my original expression with my new values in order to figure out how many bags are needed. So to solve the second half, we're now looking for the number of bags needed if we know that in this case k is 1/3. And now they want us to deal with 200 square feet. And a depth of 4 inches. Well, 4 inches is 1/3 of a foot, so we'll do 1/3 here as well. And so ideally what we get here when we multiply this out is, not 200, is 22.2 bags of mulch. So essentially they would need at least 23 bags.